Before we continue with a few more examples, I'd like to look at this equation using ideas that we know already to try to make this new trig notation fit in, and also to give us a little bit of an idea of some helpful things we see when we look at complex numbers in trig notation. The equation x cubed plus 1 equals 0. We know from polynomials that this will have 3 zeros. Knowing about our graph, it has one intercept at -1, and it has two other complex zeros. The way I'll solve this equation will be with factoring, using my sum of cubes formula, although it's not mine, it's everyone's. X plus 1 times x squared minus x plus 1. We know from this factor we'll get our first zero at -1, exactly what we saw for the x-intercept. This factor will give us the complex zeros. Plugging into quadratic formula, 1 plus or minus radical -3 over 2. I'm going to write this more in that a plus bi form where I can clearly see the real part and the imaginary part. So I'm looking at the three zeros, x equals -1, and then the two complex zeros, 1/2 plus radical 3 over 2i, and 1/2 minus radical 3 over 2i. Now each of these numbers we can plot on that coordinate plane using real and imaginary axes. When it comes to a number that appears just to be real because it only has the real part, no term with I, we could think of that as a -1 plus 0i. With no imaginary term, it's like it has a coefficient of 0, so we'll know exactly to use a -1 horizontal and a vertical component that is 0. That will be a point right on the x-axis. So let's look at where these points end up. There's -1 on the real axis with no imaginary part. What was our second point? Positive 1/2 plus radical 3 over 2i. There is that point horizontally by 1/2, vertically a positive radical 3 over 2. And where's our third point? Positive 1/2 with a negative radical 3 over 2. We see some interesting symmetry among these points. Let's draw in the unit circle because each of those points does land on the unit circle. This point -1, 0, corresponding to the complex number -1 plus 0i. This ordered pair, 1/2 radical 3 over 2, corresponds to the complex number 1/2 plus radical 3 over 2i. And same with the third point. And what do we know about the angle measures at these points? This point here, 60 degrees. Back here, halfway around the circle, 180 degrees. And this point at 300 degrees. And definitely we can see a difference of 120 degrees. Think of the full circle, 360 degrees, divided by 3, and 60 plus 120 will get us to 180. 180 plus 120 takes us to 300 degrees. 300 plus 120 is 420, but that's just 360 with an additional 60 degrees. So absolutely 120 degrees separating each of these 3 points. We'll actually see this as a law in the future. So we could use this to our advantage if we knew only that -1 was a 0, and we know there have to be a total of 3, means 120 degrees away. Move 120 degrees, we'll find the second root. Move 120 degrees further, we'll find the third root. And this is going to be very useful when we deal with powers and roots of complex numbers.